Alrighty, so today we're going to talk about the domain of our trig functions. This is page 15 that we're starting on. We have our old buddy that we met last week, our unit circle on the very front. And remember, we talked about sine and cosine as being related to the x and y coordinates on the unit circle for our given theta, right? For our given angle measure. So if I take a look at my unit circle, okay, we saw this again. We've seen this before. This is not the first time we're seeing the unit circle. It's our friend back again. So if I were talking about an angle measure of, let's say, pi over 6, right? That would be this rotation, initial side, terminal side. And that would correspond to the point on the unit circle. Remember, unit circle has a radius of 1. So this side is 1, right? All of these are 1. Unit circle, the radius is 1. That would correspond to this point on our unit circle, which has the coordinates root 3 over 2, comma 1/2. And again, last week we talked about how those coordinates for all of the coordinates that we're seeing here can relate back to, if I were to drop a side down to the x-axis and form a little right triangle, we can relate all those points back to segments from our special right triangles, our 30, 60, 90 triangles, and our 45, 45, 90 triangles, special right triangles. So the sort of last big topics that we're going to talk about, and our topic for today is the domain of these trig functions. What x values can I have? What x values are okay? Are there any places where I would be undefined? Okay, and we did see a handful of examples in our some of our practice problems earlier in this unit where we got undefined values for some of our problems that we were working on. So what we want to start with when we talk about domain is, are there any places where we're going to have problems? Okay, for sine, cosine, tangent, secant, cosecant, cotangent, are there any places where we're going to have problems? So let's start with sine. Remember, sine, okay, sine of x, right? We talk about domain, we talk about x values. Sine of x, okay, would be values for theta, like those angle measures, right? So we're still going to keep with our pi over 2, pi over 4, 3 pi over 6, whatever the case may be. I guess you would do 3 pi over 6. 3 pi over 4, stuff like that. Values, right? That would give me an undefined. Remember, so sine is our y value. Are there any points on the unit circle where I cannot have a y value? Are there any points on the unit circle where I cannot have a y value? No, right? I have no problems. So give the values of theta that would make each function undefined. For sine, there are none. For cosine, remember, cosine is our x coordinate. Are there any points on the unit circle where the x coordinate is going to be undefined? No, right? You can have an x for any of those places. Cosecant is the reciprocal of sine. It's 1 over sine, right? Which means it would be 1 over the y value. Are there any places where cosecant would be undefined? Yes, there are. Any places where y is 0, right? So where on our unit circle do we have y values that are 0? At, right, this guy right here and this guy right here. So 2 pi, also 0, and pi. So 0, pi, 2 pi. I could keep going around, right? We talked about that last week too. I could go around more than once. So if I started at 0, that's undefined cosecant. At pi, undefined cosecant. At 2 pi, or 3 pi, at 4 pi. And we could keep going as many times as I want to circle around. We could also have our clockwise rotation. So at negative pi, at negative 2 pi, at negative 3 pi, at negative 4 pi. There are lots of places. They repeat, but there are lots of places where cosecant is undefined. Let's talk about secant now. Remember, secant is 1 over cosine. So that's 1 over x. Are there any places where secant will be undefined? Sure, anywhere that x is 0, right? Anywhere the x coordinate is 0. So where on our unit circle is the x coordinate 0? At pi over 2 and at 3 pi over 2. So this will be undefined at pi over 2, at 3 pi over 2, and then remember we could keep going. So pi over 2, 3 pi over 2. This would be 5 pi over 2 if I go around again, and 7 pi over 2, and 9 pi over 2, and we could keep going, right? Round and round and round. We could also have those negative angles, right? Negative pi over 2, negative 3 pi over 2. Negative 5 pi over 2, negative 7 pi over 2, negative 9 pi over 2. We can go round and round and round in a clockwise direction. Now let's talk about tangent. Tangent, remember, is sine over cosine. So we are looking at the y value over the x value. It's that ratio of sine to cosine. Will tangent ever be undefined? Yes, tangent will be undefined when the x value is 0, right? When cosine is 0, when the x coordinate is 0. That's going to be the same places that secant was undefined. Does that make sense? Because it's x, that's our problem here, right? Where x is 0. So that's the issue here where x is 0. It's the same issue here for secant. So tangent is going to be undefined in all the same places that secant was undefined. So at pi over 2, at 3 pi over 2, at 5 pi over 2, so on and so on. And then at negative pi over 2, at negative 3 pi, pi over 2, at negative 5 pi over 2, and so on and so on. Cotangent is the reciprocal of tangent, which means that we're looking at cosine over sine. So we are looking at x over y. Are there any places where cotangent would be undefined? Yes. Cotangent is going to be undefined anytime that y is 0, anytime the y coordinate is 0. Well, that will be the same places that cosecant was undefined. So cotangent is undefined at 0, at pi, at 2 pi, at 3 pi, so on and so on. Also at negative pi, at negative 2 pi, at negative 3 pi. And again, we could keep going around as many times as we wanted to. So let's talk about the domain of these functions, but let's limit it to one cycle, right? One circle. Let's limit it to 2 pi, between 0 and 2 pi. Let's talk about what the domains of these functions would be. So for sine, we had no values to exclude, right? We didn't have any places where sine was undefined. So our domain on the interval from 0 to 2 pi, right? We're looking at the interval from 0 to 2 pi. Our domain then would be everything in that interval. Sine can take any value from 0 to 2 pi. Cosine also had no restrictions. Cosine is not undefined anywhere. So the domain for cosine would also be 0 to 2 pi. Cosecant had some problems. Cosecant had problems. We had values to exclude for cosecant. We have to exclude 0, pi, and 2 pi on the interval from 0 to 2 pi. We don't need any of the others, right? Because we restricted our domain. So that means our domain for cosecant would be, with a parenthesis, 0 to pi, since I can't be 0, and we can't be pi, and then pi to 2 pi. Again, parentheses, because I cannot have any of these values. For secant, we have to exclude any place where the x value is 0. So that's pi over 2 and 3 pi over 2. So our domain would be 0 to pi over 2. 0 gets a bracket because we can have 0, but pi over 2 needs a parenthesis because I cannot have that value. We're undefined there. And then pi over 2 to 3 pi over 2. Again, parentheses because we're undefined at those places. And then 3 pi over 2 to 2 pi. We get a bracket at 2 pi because 2 pi is okay. I would like you now to write down the domain for tangent and cotangent. Again, remember we're sticking between 0 and 2 pi. Okay, check these with me. Tangent should have the same domain as secant because again, the problem will be if x is 0. So this would be 0 to pi over 2, pi over 2 to 3 pi over 2, and then 3 pi over 2 to 2 pi. Bracket at 0, bracket at 2 pi, parentheses everywhere else. And then cotangent will have the same domain as cosecant, because again, the problem there would be anywhere that y is 0. So your domain here would be 0 to pi, and then pi to 2 pi, all parentheses, because we can't have 0, we can't have pi, we can't have 2 pi. Now, let's open this up. Let's talk about how to write that domain if we open it up. Any value. So we could have negative angles, we could have positive angles greater than 2 pi. How could we open this up if we do not restrict our domain? Well, sine and cosine are easy, right? Sine and cosine could be anything. So how would I write that? How would I write the domain if the domain could be anything? All real numbers, negative infinity to positive infinity. Always parentheses for infinity. The rest of our values get a little bit tricky because we don't have a finite amount of values to exclude, right? 2 pi, 3 pi, 4 pi. I could just keep counting by pi's, right? And if we've got negative angles, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. I could keep going on and on and on and on, okay? When I have an infinite amount of values to exclude, instead of writing interval notation like we have before, like these guys, what we're going to do instead is say all real values except 4. So for cosecant, we would say all real numbers excluding and we need to exclude 0, pi, 2 pi, negative 2 pi, 3 pi, negative 3 pi, 4 pi, negative 4 pi. So we can write that as k pi for k integers. For all integers, okay. That would scoop up 0. So 0 pi is just 0. We excluded that. If k is 1, we get pi. If k is 2, we get 2 pi. If it's 3, 4, 5, integers also includes those negative whole numbers. So negative pi, negative 2 pi, negative 3 pi, so on and so on. For secant, we want to make sure we exclude all the multiples of pi over 2 and 3 pi over 2. So again, we're going to say all real numbers excluding, this would be pi over 2k. But this time I have to be a little bit more specific. K can be any odd integer. Why couldn't it be an even integer? Why did I have to restrict it to odd integers? Mm-hmm. So why do the evens not work? Yeah. If I use an even integer, like let's say I let k be 2. 2 pi over 2 is just pi. We don't need to exclude pi. 4 pi over 2 is 2 pi. I don't need to exclude 2 pi. So if k is an even number, I would be excluding a value that I don't need to exclude. So I need to restrict it to those odd integers. Go ahead and give me the domains for tangent and cotangent. Give me the domains for tangent and cotangent. Again, tangent would have the same domain as secant. Cotangent will have the same domain as cosecant. They have problems in the same places, so they would have the same domain. Now I'm going to take a look at these on your calculator. So we're going to graph the function sine of x. So go ahead and get out your calculator for me. And let's graph the function sine of x. And I'll pull my calculator up here too. So let me pull my calculator up here. I'm on a graph page. And we're going to graph sine of x. Remember, we have our little button over here for our trig values. I believe if you use the keypad and type in sin and then in parentheses type x, I believe it will just give you sine. But you do also have your trig key here. So I want sine of x. Sine of x. Now, our x-axis is scaled by ones, like it typically is for any other function that we would graph. But I want you to remember that we looked at a lot of things that happen in multiples of pi, right? Or like fractional parts of pi. So we know for sine we've got 0 here. 0 is 0, whether it's 0 pi or just 0, right? That's still 0. 0 pi is 0. So our sine function value is 0 when our x value, when our like degree angle would be 0. But we don't talk about like 1, we talk about 1 pi or 2 pi. So if we talked about, let's say pi over 2 had a nice sine value. Sine is 1 at pi over 2. So we notice our function value is 1 when we're a little past 1, because pi over 2 is a little more than 1, right? Pi is approximately 3.14, so divide that by 2, and I'm getting something a little bit bigger than 1. And then we're back down here on the x-axis when we're, let's see, 1, 2, just past 3, right? That should make sense because sine is defined again at pi. Sine is a nice value. Sine is 0 again at pi from our unit circle. So we're seeing all that here, but we're seeing it in a little bit different scale than we're used to. So if we talk about domain for our function graphed on our calculator, we said the domain is all real numbers. So the inputs for this function, anything I want. Does that seem to jive with what we have here? Does that make sense? I could have any, yeah, it just oscillates up and down, right? Up and down, up and down. And it's going to keep doing that forever. Okay, we're going to keep oscillating between function values of +1 and -1. If I asked you the range, right? What are the y values you could have here? We're not focusing on range in this unit. But if I asked you about the range, something between -1 and +1, right? We're just up and down, oscillating between those two y values, up and down forever. Okay. Now let's go ahead and, without deleting this graph, I want to add in the graph of cosecant. So I'm going to hit the tab key. I'm going to hit the tab key so I get my entry line again. And then I want to graph cosecant. Cosecant. That's, remember, the inverse of sine. So I want to graph the cosecant of x. We talked about how cosecant was going to be indefined regularly, right? Cosecant is going to be undefined regularly. Do we see places where cosecant is undefined? We sure do. We see vertical asymptotes again, right? We talked about vertical asymptotes in our last unit. We're seeing vertical asymptotes again here, okay? Again, since this is not by like parts of pi, it's a little bit maybe more difficult to translate to those angles that we talked about, to those values that we talked about a minute ago. But can we see, again, we have vertical asymptotes. I've got a vertical asymptote at 0. I've got a vertical asymptote just after 3. That would be about pi. I've got a vertical asymptote here, again, a little further after 6. That'd be about 2 pi. I've got a vertical asymptote here just past -3. That'd be about -pi and about -2 pi. Okay. And then I want you to look at my f of x values, right? Our sine values when our red graph, our g of x or our cosecant graph has an asymptote. So we have an asymptote on the red graph about here. What's the value, the function value on the blue graph? not the x value, the function value. So it's negative pi comma 0, right? So anywhere, like we talked about, anywhere that sine is 0, right? Sine is 0, sine is 0, sine is 0, sine is 0, sine is 0. Anywhere that sine is 0, we're seeing an asymptote in the same spot with cosecant. I am not sure if we can adjust. I don't know if this will let us do. I don't know if this will let us do pi for a scale. Is this my pi key? Let me see if it'll let us. Sort of, it gives us decimal approximations. So we can see pi about there, and this would be about negative pi. So your graphing calculator can give you those approximations if you wanted to see. But if we looked at another graphing utility, I've talked about Desmos just once or twice. Let me pull up Desmos here. The SAT, now that it is digital, Desmos is the graphing and calculator function that's embedded here. If I graph sine of x and cosecant of x, and again, I'm just typing those in. I believe if you access your calculator down here in your functions, maybe you have, yep, there's our trig functions. If you wanted to get them from there, you could. What I like about Desmos is we can see the same things, but then if I go to my little like wrench here, there is an option somewhere for step. It'll be right here. If I type in pi, it will relabel my x-axis with those pi values. So we can see my asymptote right at pi, right, or negative pi, negative 2 pi, at 2 pi, and I could keep going to all my multiples of pi. So you guys can still use your graphing calculators, your TI Inspires, when you go to take the SAT, those of you who are juniors. But Desmos is embedded and it lets you change the scale a little bit easier than your calculator does. Okay. Now, what if instead of sine and cosine, or sine and cosecant, I graphed cosine and secant? Where would you expect, what would you expect to see, okay, on your secant graph? What do you think you're going to see? So for, here's in blue this time is our cosecant graph. And we saw all these vertical asymptotes. Anywhere we talked about it being undefined, what do you think is going to happen on your secant graph? The exact same thing, right? So if I got rid of sine and cosine and we graphed instead sine and cosecant, there we go. And I graphed instead cosine and y equals secant. Same thing. Right? Notice our cosine graph, up and down, just like sine, except for it has its y-intercept at 1 instead of at 0, which should make sense because cosine is 1 at 0, and cosine is 1 at pi over 2, right? But we see those same places. Anywhere that cosine is 0, secant has a vertical asymptote. Secant is undefined. Questions for me for today? And then just because we've got some time, let's look at tangent and cotangent. Those are the only ones we haven't graphed. Tangent looks a little bit different. Tangent is filled with these like squiggly increasing bits, right? Lots of vertical asymptotes, but we're not oscillating up and down for tangent like we were for sine and cosine, okay? For cotangent then, lots of these squiggly bits, but this time they're decreasing. okay? And notice, so cotangents in red, notice it's undefined anywhere that tangent is 0, which should make sense. Undefined anywhere that tangent is 0. Now let's get rid of tangent and or cotangent, and let's look at sine and cosine together. So sine and cosine look pretty much the same. They're just shifted off of each other, right? And then tangent, we see, is undefined, anywhere that cosine is 0, which should make sense. Tangent is sine over cosine. So if cosine is 0, tangent is going to be undefined. And then we've got places where tangent is 0. That matches with anywhere that sine is 0. So these should all make sense, how those domains fit together, okay? Questions for me for today? All righty.